Hi guys, welcome back to my channel. Today we're going to be looking at some applications of vectors, and we're going to be looking specifically at collision problems, or problems where time is involved. So what we're trying to see if two particles or two boats or two objects are going to reach the same point at the same time. So if they do, then it's a collision. If they reach the same point but it's not at the same time, then it's a crossover. So they're crossing paths but they're not colliding. So let's have a go at this question here. The paths of two model sailboats are defined by the following vector functions of time, where time is measured in minutes and distance in meters. Calculate if at any given time they are in the same location, that is, determine if there is any possibility of a collision. Okay, so the question here, first of all, time is measured in minutes, but it's then also telling us that calculate time in seconds, so I think that's a little bit confusing. So what we might actually do, we might just can that, and we might just say that that's going to be in minutes as well. Okay, so the first thing that I want to do, because I'm trying to see if they cross over at the same point, I'm going to equate each of the x and the y components. For my first boat, so this is going to be my x components. So for my first boat, I have t plus 13 is equal to x. And then for my second boat, I have 3t take 5 is equal to x. Alright, so just rearranging this equation now. So we're going to have 18 is equal to 2t, and therefore t is equal to 9. So they reach the same x component at t is equal to 9. So now what we can do, we can see that if this is the same for the y component, it means that they are going to collide. So for my y components, for my first boat, we have 6t, and then for my second boat, I have 5 plus t. Okay, so rearranging this, we get 5t is equal to 5, and therefore t is equal to 1. Okay, so they reach the same x component when t is equal to 9, and they reach the same y component when t is equal to 1. So they're not going to collide since they're not reaching the same x and y components at the same time. Let's have another go. Here we have an example of two particles that are actually in 3 dimensions. So now we have the I, j, and k, or x, y, and z components that we have to determine if they have the same value for time. So let's start off looking at our x components here. Now I do have a graphics calculator sitting in front of me, so I'm not actually solving a lot of these quadratic equations by hand. I will be solving them by inputting them in on the polynomial function through the graphics calculator. So for my x components, looking at my first particle here, we have 144 take t squared is equal to t squared take 5t take 6. So rearranging this now, we get 2t squared minus 5t minus 150 is going to be equal to 0. So when I chuck these values of a, b, and c into my graphics calculator in that equation solver, I get two values for t. So the first value that I get for t is negative 7.5, and the second value I get for t is positive 10. Now automatically we can discount the first value because it doesn't make sense for us to have negative time. Okay, so let's go ahead now, let's look at the y component. And again, what we're looking for with this y component is that the y component is going to have the same time or be in the same place at the same time. So we're looking for this value where t is equal to 10. So let's have a look at my y components now. So we have 2t squared is equal to 240 take 4t. So rearranging this, I'm going to get 0 is equal to 2t squared plus 4t minus 240. And we can simplify this by dividing through by 2 because all of the terms are even terms. Okay, so chucking this into my graphics calculator, I get two values. I get a value of t is equal to negative 12, or I get a value of t is equal to, oh good, or t is equal to 10. Okay, so automatically again we're going to discount this first value because we don't want negative time, and again we can see here that t is equal to positive 10. Now we're going to do the same thing with our k component. So here it's a little bit more complicated because we do have a cubic function that's involved, but I'm going to use my rule for expansion from Pascal's triangle. So if you are not familiar with that, when we have a quadratic equation, the coefficient of the quadratic terms are going to be 1, 2, 1, and we have reducing powers of x. So if we had, say for example, x plus y squared, this would become 1x squared plus 2xy plus 1y squared. So if I have x plus y cubed, this is now going to become 1, 3, 3, 1. And again, we're going to have those reducing powers of x. So this is going to become x to the power of 3 plus 3x squared y plus 3xy squared plus 1y cubed. So I'm just following this pattern when I do this expansion, and then I'm going to go ahead and multiply by 0.25. I can use the same pattern to expand the quadratic on the other side. Lastly, I'm going to rearrange, so I'm going to bring everything onto this side. So we have 0.25t cubed minus 1.5t squared minus 1t squared, so we get negative 2.5t squared. Then we have 3t. When this comes over, it'll be plus 8t, so that's going to be plus 11t. And then we're going to have negative 2 minus 16 minus 92, and we're going to get negative 110, and that's equal to 0. And again, all I do when I solve this, I'm just putting this in my graphics calculator. I'm not actually solving this by hand. So when I chuck this in my graphics calculator, I'm going to put in the coefficients. So this would be my value for A, for B, for C, and for D. And I get a value of t is equal to 10. Okay, so that tells us that we do actually have the particles colliding. So each of these actually reaches the same location when t is equal to 10. So let's go ahead now. Let's substitute back into that original expression to determine when the equations are actually equal to one another. So I've gone ahead and substituted into my first equation, and I get a vector equation of 44i plus 200j plus 128k. So now we're just going to do the same thing with the second particle, just to show that they are indeed at the same spot. So here we have 100 minus 50 minus 6, which is going to give me 44i, plus 240 minus 40j. So plus 10 minus 4 would be 6. 6 squared is 36. 36 plus 92 is going to give me 128k. Okay, so the points do match, and they do actually collide in this case. And this is because they are reaching the same component, the x, y, and z components, or the I, J, K components, at the same time, so when t is equal to 10. Alright guys, so this is just one application of vectors, so using vectors to solve collision problems. We're actually going to go into a very similar video in the next lesson looking at position vectors. Alright guys, I'll see you in the next one.